Okay, welcome to Psych 200 research methods. Today we're talking about experimental research. Actually, we're going to be talking about experimental research for a few weeks. This is just the first chapter. I've broken it up into several chapters. This is chapter 6A, and there's going to be 6B, and then there's going to be some more stuff. Okay. So anyway, let's get started. Let's talk about experimental research. What is the goal of the experimental research study? What do we do with an experiment? The main reason you do an experiment is because you want to establish the existence of a cause and effect relationship. Okay, you want to say that one thing causes another. Okay, cause and effect relationship between at least two variables. It could be more. Okay, that is the most important part of an experiment. What really sets it apart from the other types of research. It's the only kind of research strategy that allows you to really say something about cause and effect. Okay, an experiment, a true experiment, must demonstrate that changes in one variable are directly responsible for causing changes in a second variable. So for instance, changes in the amount of alcohol consumed, for instance, cause changes in behavior, right? We can show that with an experiment. And we'll talk about examples like that. Let's keep going. There are four basic elements of an experiment. Okay. First, an experiment must have manipulation. That means you have to do something, okay, to someone. Okay. Manipulation. Okay. The research manipulates one variable by changing its variable to create a set of two or more treatment conditions. That sounds complicated. What that means is you're going to be doing something, okay, to do something to your participants. You're going to vary, for instance, the amount of alcohol they get, okay, so that you can get them drunk, okay? That's manipulation. Or maybe you're going to anger them. Maybe you're going to subject them to exercise. You're going to manipulate something. You're going to do something to them, okay? This is the only type of research where you actually do something that involves a manipulation. All the other ones, you really just measure, okay? And of course, an experiment also involves measurement. After you do a manipulation, okay, after you do something to participants, you're usually going to measure something, okay? A second variable is measured for a group of participants, resulting in a set of scores in each treatment condition. So you manipulate something like the amount of alcohol participants get, and then you measure something else, like their aggression, okay? So it involves manipulation, it involves measurement, it involves other things as well. It involves comparison. Okay, the scores in one treatment condition are compared with the scores in another treatment condition. So it involves comparison. You're going to compare the participants that consumed alcohol, for instance, those in the treatment condition, with those that did not consume alcohol, those in the control condition. Okay, so it involves comparison. You create different groups and you compare them. It also involves control. All other variables are controlled to be sure that they do not influence the two variables being examined. That fourth one is important. By control, what we mean is that we don't allow other things, or we should not, we try not to allow other things to have an effect on the outcome of the experiment. So we're going to control things, maybe like temperature, you know, the environment. Experiments are usually done in a laboratory that is kind of a sealed off environment where we don't allow other things to happen. So while we're getting our participants drunk and then hoping that they become aggressive, right, we do not allow other things to happen, like, you know, their friends stopping by to distract them. Or we don't allow, you know, for instance, music to be played that might also distract them. We don't allow anything else to have an effect. That is control, okay? And control is very important. That is how we know that one thing leads to another. Alcohol is actually what caused aggressive behavior, because we didn't allow anything else to have an effect. We didn't allow any distractions. We didn't allow anything else, for instance, to anger them or anything else to have an effect. That control is important, okay? Without the control, you cannot be sure about that cause and effect relationship. Okay, let's keep going. Statistical significance. When you do an experiment, you have to be concerned about statistical significance. Actually, you're always concerned about statistical significance, okay, for most research, but especially with an experiment. So before you can interpret that differences between treatments as a cause and effect relationship, you must conduct a hypothesis test and demonstrate that the difference is statistically significant. Let me explain that. What that means is when you do an experiment, you're going to compare groups, okay? You compare the treatment group, let's say the control group. You're going to compare groups. And before you know if you have a cause and effect relationship, that alcohol, right, those that consumed alcohol really are more aggressive than those that did not, right? Before you know that, you need to do a hypothesis test, okay? And with a hypothesis test, you know, well, you're comparing these groups, right? You do a hypothesis test to demonstrate the difference is statistically significant. So you compare the groups to determine if it's a real difference. We talked about hypothesis testing when we talked about statistics. Okay, but all that means is you're going to compare the groups and you need to determine that there's a real difference between them, that it is statistically significant. And you determine that with a hypothesis test. Is the difference real, or is it non-significant? Is it something that is more likely to basically provide, let's say, support for the null hypothesis, which says there are no differences? Remember, we talked about things like that. Okay, so statistical significance is determined by comparing groups, right? Doing a hypothesis test, right? And determining that the difference is actually real, okay? That it's big enough to matter. Let's keep going. More about statistical significance. What does a statistical significant difference mean? Or what is a significant result? I told you guys already, but here's more about it, right? With a significant result, we mean that the difference is large enough and consistent enough for a hypothesis test to rule out chance as a possible explanation. The difference is big enough to matter. The difference is big enough so that it probably did not occur by chance. Remember, the null hypothesis says that the difference is zero or small enough that it's probably due to chance. When you have statistical significance, when you have a significant results, that means that that is unlikely. Okay, that means that the difference is large enough that it probably was not due to chance, that you should reject the null hypothesis. Therefore, the difference must have been caused by the treatments. So if it's not due to chance, it must be due to the treatment. And in our example that we're talking about here, the treatment being alcohol. Alcohol must have caused the aggression, right? The difference in aggression that we see. Let's keep going. We're making experiments, by the way, sound really complicated, but in principle, they're not really complicated. They are complicated when you try to do them, but the logic is not complicated. There's different terminology that you need to know for an experiment, and you probably heard about some of this from Psych 101. But in an experiment, yes, you need something called an independent variable. Your independent variable is the one that you vary, the one you manipulate, okay? An example would be exercise. So you're going to vary the amount of exercise that, say, participants get. You know, and keeping with the example that I already been mentioning, maybe you're going to vary the amount of alcohol that you get participants, or you can vary the amount of marijuana that they get. You can vary, for instance, the amount of frustration. You can vary all kinds of things, but your independent variable is the one that you vary, right? The one you manipulate. Okay, so that you're hoping something happens to the participants, okay? That it does something to the participants. Now that's the independent variable. A treatment condition is a situation or environment characterized by, oh, well, I left out some writing there. So a treatment condition is basically a feature of the independent variable. A treatment condition is basically when you, a group that you create from varying the independent variable. So there's some text left out there, so I have to explain this, okay? So the independent variable is like the exercise, let's say, that you vary. The treatment condition would be a situation of the independent variable, like no exercise, for instance. So if your independent variable is exercise, you can create a treatment condition called, no exercise, okay? And then you could create another one that is exercise. So a treatment condition is basically a situation, that has to do with the independent variable. I'll give you another example. The independent variable could be alcohol, and you can vary the amount of alcohol. So alcohol, no alcohol would be treatment conditions. You can create different treatment conditions. And levels are different values of the independent variable. You can have different levels of the independent variable. You can have high alcohol, right? Medium amount of alcohol, low alcohol, or in keeping with this example that we have written here, there could be a high amount of exercise, medium amount of exercise, low amount of exercise. Those are the levels, okay? Not sure what went wrong there with the text where something got cut off where, you know, the explanation for treatment condition isn't clear. But a treatment condition is a condition of the independent variable, okay? Levels are when you have high, medium, low, you know, something like that in a certain order. Let's keep going. I don't want to confuse you guys any further. With an experiment, you need also something called a dependent variable, or a DV, right, as an abbreviation. A dependent variable is the variable that is observed for changes to assess the effects of manipulating the independent variable. Let me explain that. The dependent variable is the variable that you measure afterward, okay? So the independent variable is the one that varies, the one you manipulate, and then the one you measure afterward is called the dependent variable. So if your independent variable, let's say, is exercise, that's what you're varying, okay? Then the one you can measure afterward, your dependent variable, can be weight, okay? Or if you're varying the amount of alcohol, your dependent variable can be aggression. That's what you measure afterward. So that's the dependent variable. It's the one that you measure afterward. And there could also be extraneous variables. Extraneous variables are other variables in the study, other than the independent variable, other than the dependent variable. Other things that are extra, okay? It could be diet, medication, genetics, all sorts of things, okay? Those are extraneous variables. Those are other things that could possibly have an outcome, could affect the outcome of the experiment. And you're going to want to control those extraneous variables, and we'll talk about that. Let's keep going. Controlling nature. I mentioned control already a little bit, but here's some more information. An experiment, remember, involves control, okay? An experiment must control the nature to establish a cause and effect relationship. So an experiment must control those extraneous variables. It must control other things, okay? The two variables being examined must be isolated from the influence of other variables. The exact character of a relationship must be clear. So we must control the variables. We need to make sure, right, that our independent variable is what is causing our dependent variable. We want to control the other extraneous variables. We want to control maybe things like temperature, things like mood, other things that could possibly have an effect on the outcome of the experiment. If, for instance, we're determining the effect of exercise, let's say, on weight, we want to control other things. We want to control the things like diet, genetics, if it's possible, you know, maybe medication, all sorts of other things that could possibly affect weight, okay? We only want exercise to affect the weight, okay? So that's important for an experiment. You must control the other things, okay? Otherwise, the cause and effect relationship will not be clear. Let's keep going. Other things about an experiment. So the basic goal of an experiment is to demonstrate a cause and effect relationship, okay? You must demonstrate that the cause happens before the effect, okay? There's just a few logical things here, okay? If you want to make sure that your independent variable causes changes in your dependent variable, that means logically that the independent variable must be manipulated before anything happens with the dependent variable. So you must first, let's say, have participants exercise and then measure their weight and then weigh them, basically. Or if you're determining the effect of alcohol on aggression, first you give them some amount of alcohol, depending on which treatment condition they're in. And then you provide them with an opportunity to behave aggressively. So that's just logical. The independent variable should come before the dependent variable, because the independent variable should be causing changes in the dependent variable, okay? you must also establish that one specific variable is responsible for changes in the other variable, right? That it's only the independent variable that's causing changes in the dependent variable, right? An experiment must rule out the possibility that changes are caused by extraneous variables. So we must rule out those other extraneous variables. I've said this before, it's kind of redundant. Let's keep going. There are problems that you can have with an experiment, and we've actually mentioned these before when we talked about correlations and things like that. So with an experiment, you might have, the experiment actually can solve problems, right, that we talked about before. And one of these is the directionality problem, okay? A research study must establish a relationship between two variables, okay? And the existence of a relationship does not always explain the direction of a relationship. Just because there's, let's say, a relationship between, let's say, between exercise and weight, doesn't mean you know clearly that it's the exercise that's affecting the weight. Maybe weight is affecting exercise. Maybe those that weigh more find it difficult to exercise. So we need to establish what is causing what. Is exercise causing changes in weight, or is weight causing changes in exercise? When you just measure things, you don't know the direction of the relationship. Okay, so the remaining problem is to determine which variable is the cause and which is the effect. And when you do an experiment, you solve this problem. You have participants exercise, okay, and then you measure their weight. Okay, one comes before the other, and you see if changes are caused. Okay, if there's a significant effect. So remember, the directionality problem is when you have a relationship between two variables and you don't know which is causing what. They're related, but you don't know what's causing what. So you can use manipulation to determine the direction of cause and effect, like I just said. Here's an example, okay? And this is an example I think that we mentioned before when we talked about correlations. There's a relationship between ice cream consumption and temperature, okay? Believe it or not, there's a relationship there. So it says there, figure 7.2, ice cream consumption and temperature rise and fall together, okay? So as ice cream consumption goes up, temperature goes up, or as temperature goes up, ice cream consumption goes up, whatever way you want to mention it, right? But they go up together, they fall together. When it gets hotter, ice cream consumption goes up. When it gets colder, ice cream consumption goes down, okay? Now, what's causing what, okay? Are changes in temperature causing changes in ice cream consumption? We can do that experiment to figure this out, right? We can put participants in a room, okay? And there's a refrigerator in the room with some ice cream, okay? And we can raise the temperature, right? And we can tell participants, oh, by the way, there's some ice cream here in the room, right? In this refrigerator that you can have to cool yourself down. So we can raise the temperature and then see, how much ice cream is consumed. We can also lower the temperature, create a different treatment condition, and then see what happens to ice cream consumption. So we can vary the temperature to see how it affects ice cream consumption. And what we'll probably find is that the temperature is causing the changes in the ice cream consumption. Now, we can try to do the experiment the other way, perhaps, right? We can vary the amount of ice cream consumption. We can give a lot of ice cream to some people, and let's say very little or maybe no ice cream to other people, and then see if it causes a change in temperature in the room. And when we do that, we will probably find that eating ice cream is not going to cause the temperature to go up in the room. It'll probably cause temperature to go up in your body, to go down in your body, but it will not affect the temperature in the room. So eating ice cream will not cause a decrease, let's say, of the temperature or an increase in the temperature in the room, okay? It doesn't make sense that way. So we can use an experiment. The point is we can use an experiment to determine the direction of the cause and effect. We can manipulate both variables, okay? And see which one causes changes in the other. We can manipulate first temperature and see if it affects ice cream consumption, or we can manipulate ice cream consumption and then see if it affects temperature. And we'll find that temperature affects ice cream consumption, but ice cream consumption does not affect temperature. So an experiment allows us to solve the directionality problem. There's also the third variable problem, which we mentioned before when we talked about correlations. The third variable problem is when you have a study that establishes that two variables are related, but it doesn't necessarily mean that there's a cause and effect relationship between them. There might be a third variable that is responsible for producing the observed relationship. So here's the thing, the third variable problem, you have two things that seem to be related, okay? But they may not necessarily be causing each other, or one may not cause the other. They may not be a cause and effect relationship between them, okay? There might be a third thing that explains the relationship. And let me give you an example so you understand. Here's an example of the third variable problem. So here's the thing. We have three variables here. We have temperature, we have ice cream consumption, and we have crime rate. Okay. Believe it or not, ice cream consumption and crime rate are related. When ice cream consumption goes up, so does the crime rate. When ice cream consumption goes down, so does the crime rate. So there's a relationship between ice cream consumption and crime rate. But they don't necessarily cause each other. Ice cream consumption is not causing an increase in crime. Crime is not causing an increase in ice cream consumption either. They are both explained by temperature. Temperature explains the relationship between ice cream consumption and crime rate. When temperature goes up, ice cream consumption goes up because it's hot and people want to cool down. And when temperature goes up, the crime rate also goes up because there's more people outside. And when there's people outside, they tend to, piss each other off. They tend to cause problems for each other. Like especially when it's crowded. Okay. So that's what explains the relationship between ice cream consumption and temperature. They are both related to temperature. Ice cream consumption and temperature do not have a direct relationship. Okay, they are related, by temperature. So, you can show that yes, there's a relationship between ice cream consumption and temperature, but they're both related to a third variable. So there are things like that you may notice. Another example would be, I mentioned before when we talked about correlations, is the relationship between ice cream consumption and drowning. When ice cream consumption goes up, more people drown. When ice cream consumption goes down, less people drown. Ice cream consumption and drowning, there's no cause and effect between them, okay? They are related, but there's no cause and effect. Again, they're both related to temperature. When temperature goes up, more people eat ice cream. When temperature goes up, more people go swimming, and therefore more people drown. Okay, I explained that before. So an experiment could also solve this third variable problem, okay? When you have two things that seem to be related, but they don't make any sense, okay? The relationship doesn't make any sense. It probably means that there's a third thing that explains both of them. There's a third thing that's causing both of those things. Unique elements of an experiment. Okay, so control. So you need control of other variables, right? Other than the independent, dependent variable. So yeah, you're going to manipulate the independent variable. You're going to measure the dependent variable, but you need to control other variables. This is like the third time I mentioned this. I'm just I'm being redundant here. Okay, so observed relationships must not be contaminated by the influence of other variables. Okay, you need to make sure the independent variable is the only thing that's causing changes in the dependent variable. Okay, so research must rule out other possible changes to the independent variable. You must eliminate what we call confounding variables. Other variables that are possibly having an effect are called confounding variables, and we must rule those out. And we're going to do that in certain ways, okay? That's what we're going to talk about now. So research must eliminate all confounding variables. Confounding variables, we're talking about, these are extra variables, or we call it a third variable that changes systematically along with the two variables being studied, okay? So we said there are extraneous variables before. There are things that are extra, things other than the independent dependent variable, okay? If these variables, if these other things could possibly be having an effect on the dependent variable, on the outcome of the experiment, okay, we call these things confounding variables. Okay, confounding variables are just third variables that seem to vary systematically. They seem to vary along with the experiment, with changes in the independent variable, for instance. and they might be explaining the outcome of the experiment. Okay, so these are confounding variables, and we must eliminate them. We must eliminate this possibility that there could be something else affecting the outcome. An example, not an interesting example, but an example is the effect of humor on memory. Research shows that humorous sentences are remembered better than non-humorous sentences. So things that are funny, we remember better than things that are not funny. However, there might be something else that explains that finding, that explains that outcome, okay? That experiment that was done, okay? It could be that surprise and not humor is having an effect on memory. Humorous sentences are more surprising than non-humorous sentences, right? So you see how surprise here is varying along with the independent variable? So it could be surprise that is causing the effect on memory. Things that are surprising, you remember better than things that are not surprising. So here's what we're looking at over here. A possible confounding variable. So you have humorous sentences, right? On the left, right? Something that is humorous is also surprising, and that causes high memory scores. And then on the right, you have things that are non-humorous, which also happen to be not surprising, and they cause low memory scores. So what's actually causing, the memory scores that we see? Is it the fact that is it humor or is it surprise? Is it the difference in humor or a difference in surprise? See, we don't know. That's a confounding variable, right? Surprise is a potentially confounding variable. So how do we solve that problem? Okay, we'll talk about that. So an extraneous variable becomes a confounding variable only if it influences the dependent variable. Okay, so an extra variable, something else, right, is a problem only if it influences the outcome of the experiment. Only then is it a potential confound. Something totally unrelated is not a threat. Something else, right, that doesn't affect memory is not a threat. Okay, so maybe the color shirt you're wearing, probably does not affect your memory. Okay, because that's not what you're being asked about. You're being asked to recall some sentences, right? The color clothes that you're wearing, right? That could vary, but probably not having an outcome on memory. Now, how surprising the sentences are, that could be having an outcome. Okay, so an extra variable, something else other than the independent and dependent variable, is only a confounding variable if it influences the dependent variable, if it influences what you measure, right? What you're measuring, okay? The outcome of the experiment. A confounding variable must vary systematically with the independent variable in order for it to be a confounding variable. In order for it to be, a confounding variable, it must vary systematically, just like surprise varies along with humor. Things that are humorous are surprising, right? That's what makes a lot of things funny to begin with. You didn't expect them, and that's why they're funny. A comedian who is predictable is not going to be funny. Okay, so surprise varies along with memory. So it varies systematically with the independent variable, right? We're manipulating the amount of humor, and surprise seems to vary along with it. And we didn't intend that. That's a confounding variable. A variable that changes randomly with no relationship to the independent variable is not a threat. So for instance, maybe the age of participants can vary randomly. So that won't be a problem. Or maybe the sex of participants, or maybe the color clothes they're wearing. Anything that varies randomly may not be a problem. It's only something that varies along with the independent variable. Systematically, it varies the same way the independent variable does. All right, let's keep going. Now, here's a way to eliminate the confounding variable of surprise. Okay, remember we talked about how surprise varies along with memory? Okay, well, here's the thing. We can tell participants ahead of time that they're going to be hearing something funny, or that they're going to be hearing something that's not funny. So we can tell them ahead of time and therefore get rid of the surprise. So we can have humorous sentences that are not surprising, and we can also have non-humorous sentences that are also not surprising. So you see, surprise now isn't varying along with the independent variable. It's not varying systematically. So now surprise is not a problem, not in this example. And we find that humorous, non-surprising sentences lead to higher memory scores than non-humorous, non-surprising sentences. Okay, so we eliminate the effect of surprise, and we still found that humor causes an increase in memory. Okay, that's an example how to eliminate a confounding variable. And we'll talk about what this is called. Okay, doing it this way. Okay, we're going to talk about those strategies right now. This is one example. Okay, so here's the way you control extraneous variables. This is the way you can get rid of these potential confounding variables. There's three primary techniques for controlling extraneous variables, and they are holding variables constant. You can hold things constant, and I'll talk about what that is, how you do that. You can match values across treatment conditions. I'll talk about how to do that. And you can control by randomization. I'll talk about that as well. Make sure I check the time, make sure that we're doing okay on time. So let's talk about how you use these techniques to basically do away with confounding variables. So let's talk about the first one, holding variables constant. This one is basically, it's easy in principle. It sounds easy, okay? Holding variables constant simply means that you make those other variables the same. That's what I mean by constant. So there are, for instance, potential environmental variables, things that can vary in the environment. Okay, you can hold those constant. When you do your experiment, always do it in the same room, so the room doesn't vary. Okay, because maybe being in a small room and versus being in a large room, maybe that has an effect on memory, let's say. Okay, you can make sure you run your participants during the same time of day, so the time of day doesn't vary, right? Maybe always run the experiment in the afternoon, let's say. Therefore, that will not affect memory scores, right? Or maybe use the same researcher, the same person running the experiment, because maybe some are more distracting than others and they have an effect on memory. You can imagine, for instance, let's say if the experimenter happens to be very attractive and the participants have to, basically remember some sentences, right? They're being tested on their memory. If they're very distracted, let's say, by the attractiveness of the experimenter, they may not do so well. Just like when you're in a class, right? And, there's someone in there that you find very attractive. So you're always looking at them and paying attention to them rather than what you should be learning. And then you don't learn very much. Okay. Those are environmental variables. So you can just hold them constant. That means that you make it so that they don't vary. Okay. There's also individual differences. People can vary themselves, right? People can vary in like gender or sex, right? Males, females, right? You can have also in between, right? People can also vary in age. Some are younger, some are older. People can vary in IQ. Some are smarter than others. And maybe they also have better memories. All those things can vary. And all those things can affect the outcome of the experiment. So how do you solve this problem? Well, you can hold variables constant, like I said, right? You make it so, these things don't vary. I talked about how to do that with environmental variables, but with individual differences, right? By holding constant, that means you only use participants of a certain gender. Now let's talk about sex in general, more specifically, because that's easier to understand. So let's say you have males and females, right? And you're concerned that maybe females have better memory than males. Okay, they are better at language on average, what the research shows, right? And you're talking about sentences, right, that they have to memorize. So maybe only run your experiment with females, or maybe only with males. That way gender doesn't vary. Or let's say age can vary. So maybe you only want to run your experiment with participants who are of a certain age. Those that are, let's say, are in their late teens only, 18 and 19, or maybe they're all 18, they're all 19. They're all a certain age or a certain IQ range. Let's say you run your experiment only with participants that are average IQ. They all have an IQ around 100. Okay, and you run your experiment only with those people. That's what holding constant means. It means you make it the same. That's what that means, okay? So if IQ can cause differences in the memory scores, okay, well then you narrow down the IQ so it doesn't vary. If it's age, you narrow down the age. If it's gender, sex, right? then you can hold that constant by not letting it vary. Okay, that's what we mean by holding it constant. Okay. Another thing you can do to deal with extraneous variables is called matching. You can match values across conditions. So you have participants, for instance, who are have to remember humorous sentences, and you have others that have to remember non-humorous sentences. You can match. Okay, you can assign males and females equally to conditions. You make sure you have the same number of males and females, let's say, in the group that's having to remember humorous sentences, and also in the group that's having to remember non-humorous sentences. Matching simply means you have the same number in each group. And if there's the same number in each group, then you can't really say that basically, in this case, sex is actually causing the effect that you see. If you, let's say, have more females in one group than another, then it could be the fact that you have more females in one group that's causing the difference in memory scores. But if you have the same number of females, same number of males in each group, then they're matched, and that can't be what's causing the scores. You can also match age so that the average age is the same across condition. The average age for those learning humorous sentences and those learning non-humorous sentences is the same. So now age doesn't really vary, right? You've matched that. You can match rooms by running half the participants in one room, half the participants in the other, right? And that way, you don't have a problem because they're matched. Okay, it's not like you have more participants in one room than another. Okay, so that can't be causing the differences. You can match the time of day, run half the participants early, half the participants late. Okay, matching simply means that the groups are going to have the same number of males, females, same number of same average age, whatever it is that could possibly vary, you match it between the conditions. And if it's matched, if it's the same for both conditions, then it's not varying by condition. It's not varying. It cannot possibly, it's not varying by condition. It's not varying systematically here. Okay, so therefore, it's not causing the outcome that you see. Matching treatments across conditions over time, by the way, is called counterbalancing. When you do this over time, right, as you do your experiment, it's called counterbalancing. So you do an experiment, you're not going to run over your participants in one day, right? You get some one day and another, and weeks go on, months go on, and you keep counterbalancing. You make sure you have the same number of males, females in both groups, that the average age remains the same. You are also matching, let's say, ethnicity, right? Make sure that you split your Black people evenly, right? Same number of Black people in the experimental group and the control group, right? Same number of white people, same number of Latinos, right? So that doesn't affect the outcome. You match the conditions. So here, when you match, right, the extraneous variables, the possible confounding variables, they're not varying along with the independent variable. So here's more information about this. Matching values across treatment conditions, right, requires time and effort. I mean, if you're gonna, let's say, match IQ, you have to measure IQ. If you're gonna match, let's say, sex, males and females, then you have to measure that. You can usually tell if they're male or female, but not always. So you have to ask them, they have to report that somewhere, right? And you have to match them. You have to ask them about ethnicity. You can't always tell who belongs to what ethnic group. For a lot of people you can, but not for everybody. So you have to measure all these things ahead of time. Okay, and it's impractical to do this for all extraneous variables. You're going to measure, let's say you measure sexual orientation. You can measure, sex. You can measure IQ, age, ethnicity. There's a whole number of things that you would have to measure ahead of time. Personality, right? That can be a whole test in itself, right? Personality can vary. Maybe that's affecting the outcome, right? All kinds of things. So it's kind of it's not very practical to do this. It's not always very practical, okay? It requires a lot of time and effort, okay? So you can do it another way. Another way to get around this problem, right, is to control by randomization. So there's a lot of variables, let's say, a lot of extraneous variables that could have an effect. You can control by randomization. So this simply means you use a random process to help avoid a systematic relation between two variables. So you make sure that sex varies randomly. Ethnicity is going to vary randomly. Age, IQ, all that stuff is going to vary randomly. If it varies randomly, then what happens is that over time, you end up with similar numbers in both groups. In your treatment group and your control group, you end up with similar numbers of smart people and not so smart people, similar number of this ethnicity, that ethnicity, similar number of males and females. Just by chance, through randomization, you can control a lot of extraneous variables because people will vary randomly. And as long as you don't have a biased way of assigning participants, if you assign participants randomly to groups, let's say you flip a coin, right? First person comes in, you flip a coin, right? Okay, so you go in this group, the other person, okay, you go in that group, and you assign people randomly, like through the flip of a coin. Then you're going to control by randomization. Over time, what you find is there shouldn't be any variation that goes along with the independent variable. It shouldn't be that age varies along, let's say, along with humor, let's say, whether they get a humorous sentence, whether they have to learn humorous sentences or not. Okay, randomization is basically just what this means is you assign people randomly to the conditions, and just by chance, it shouldn't vary. Like when you flip a coin, if you do it often enough, you should get close to half tails and half heads. Well, if you assign females and males randomly, you should get like half females, half males in both groups. Same thing with let's say IQ. You should get pretty close to the same average IQ in one group than another, just by chance, right? Because it's random. Control by randomization. So control by randomization disrupts any systematic relationship between extraneous variables and the independent variable and the dependent variable. Okay, so it disrupts any relationship. So it's not that if you assign people randomly to conditions, it's unlikely, for instance, let's say that you're going to get more smart people, let's say in the humorous sentences group than in the non-humorous sentences, or that you're going to get more males in one group than the other. It's unlikely if you do it randomly, and especially if you have a lot of participants. So it prevents any extraneous variables from becoming confounding variables. So if they vary randomly, that means they don't vary systematically. They don't vary along with the independent variable. Example is the coin toss, which I already talked about. So for each participant, right, you can use a coin toss, right? First participant comes in, okay, flip a coin. Okay, you're in the control group. Next participant, flip a coin. Okay, you're in the, in the treatment group. Let's say heads is treatment, tails is control group, right? And you do it that way. And what you'll find, if you have enough coin tosses, if you have enough participants, right, that things like age, gender, IQ, all those things will be randomized in the long run. When you have large numbers, it'll be more or less random. And you can do it all at once. Here's the thing, though. You don't really use a coin toss, okay? That's just to explain it. When you do this in real life, when you're doing an experiment, the computer does it for you. The computer generates what's called a random table. And it basically tells you, okay, participant number 1 should be in this condition. Participant number 2, put them in this condition. Participant number 3. So the computer generates basically a table that is supposed to assign people randomly. And you follow the table, you follow the order of the whatever the printout says, and you should assign people randomly. So it's not really done with a coin toss. Okay. And here's the examples we talked about. Okay. This should make it clear if it isn't clear already. So look at the columns for treatment 1 and 2 on the left. So A, okay, A right there in this table here, it says A, gender confounded. So you can see treatment 1 has 2 males, okay, and all the rest are females. Treatment 2 has 2 females and all the rest are males. There's a different number of males and females in the treatment groups. So gender, more accurate to say sex, is confounded here. The fact that you have more males than females in one group than the other, right, means that, that could be affecting the outcome of the experiment. So you can fix that by holding gender constant. So look at B, right? B, gender held constant. Treatment 1, treatment 2. You held gender constant. Now you only have females in your experiment. Nothing but females in treatment 1, nothing but females in treatment 2. In treatment 2, right? That's what we mean by holding constant. You make it the same for both groups. It's all females. Or you could have run the experiment with all males. And that way, sex doesn't vary. Or gender, as they're calling it here, right? Gender is actually something else, but this is really sex, but that's what they labeled it as. And you have C there, gender mismatched. Gender matched. You can match to avoid gender being a confounding variable. And that means that you have the same number of males and females in each group. Treatment 1 has 4 males and 6 females. Treatment 2 also has 4 males and 6 females. That's what we mean by matching. It can't be that if you find a difference between treatment 1 and treatment 2, it can't be that it's the sex of the participants that's causing that difference, because they're the same in both groups. You have the same number of males and females in each group. It can't be that that's causing anything. And D, we have, gender randomized. So you assign males and females randomly to the conditions. Treatment 1, first, it was a male, then a female, male, and it was randomly. Same thing for treatment 2. And just by chance, you should get about the same number of males and females in each group. And also by chance, the age will probably be around the same if you assign them randomly. Just by chance, the IQ will probably be about the same. When you assign people randomly, things seem to even out with large numbers. So that's an example of basically how to control extraneous variables, how to get rid of potential confounds, right? By using, the strategies called holding constant, matching, randomization. The next part, let's keep going, actually. We're not done. Let's keep going. Advantages and disadvantages of control methods, okay? Holding variables constant and matching has certain disadvantages, okay? So holding variables constant and matching requires extra effort and extra measurement. In order to hold things constant, to match, you have to measure things ahead of time. You have to measure IQ, right? You have to ask them about sex, or gender. You have to ask them about ethnicity. Like I said, you have to measure all these things ahead of time so that you can match, assign evenly, or so that you can, let's say, exclude certain people and let's say only run your experiment with those that are a certain IQ, that have a certain IQ, or only those that are male, only those that are female, or only those of a certain ethnicity, whatever it is, You have to measure those things ahead of time if you want to hold them constant, if you want to match, okay? Holding things constant also limits external validity. When you run your experiment, let's say only with females, right? You held sex constant. Well, that limits external validity. That limits your ability to generalize. So now your experiment applies to females. You didn't have any males, so you can't really say that this is what's happening in males as well. So that's a disadvantage as well. Randomization also has problems. With randomization controls a wide variety of variables simultaneously. So all at once, you can control a bunch of variables simultaneously if you, let's say, assign participants, let's say, to one of 2 groups through the flip of a coin, okay? The problem with randomization is that it's not guaranteed to be successful in balancing variables. When you assign people randomly, it's not guaranteed, for instance, that you have an even number of males and females in both groups. It could be by chance, even though you assign participants to the groups through the toss of a coin, you could still end up with very lopsided groups. You could still end up with a group that has 8 males and 2 females, and the other one having 8 females and 2 males. That can still happen. Just like when you flip a coin, you can get like 10 heads in a row. And, and if you only flip the coin 10 times, right, you can get a very uneven number of heads and tails. The same thing can happen with randomization if you have a small number of participants, which, by the way, can often be the case in experiments. Experiments are hard to do, and you're not going to do an experiment with hundreds or thousands of participants usually. Usually, you're going to have dozens of participants. You might have 40, 50, 60. you can get very lopsided numbers, lopsided distribution of males and females of IQ or age if you just use randomization. So what we actually do is we follow a table that's generated by the computer, and it tells us how to assign things, so make sure it's equal. So it's kind of what is actually done is actually matching, but through matching and randomization at the same time. Okay, and let's see if does that actually come up? No. Okay, but that's what happens in real life. That's where I'll stop. So let me go ahead and stop recording.